No, no worries. If that's our biggest problem, we're doing fine. Okay. So from C to B, this traveler has no overlap, but from B to D, they overlap with 2 other travelers. So the weighted average of that is 1.14. And it's the same exact thing for the traveler going from A to D. They have no overlap for the first leg of their trip, but then they have two units of overlap for the second leg of their trip. Okay. So what we've talked about so far is really just thinking about a single traveler going between a single OD pair, which is great. That's what we're building up from. But ultimately, the problem we're trying to solve is how to maximize total or cumulative flow overlap in the entire network, right? By changing everyone's paths. So we're given a directed graph or a network with a finite set of OD pairs. We're assuming that all of our link costs are non-negative, which is a quite reasonable assumption. We assume we're given an origin destination demand table, right? The total number of trips from each origin to each destination, as well as a finite number of acyclic paths for each origin destination pair. Okay, and then the problem, what we're trying to do is find a set of paths for each origin destination pair that maximize this network flow overlap. And we're going to make the assumption that all trips between each OD pair are assigned to a single path. Actually, due to the properties of the problem, if you drop this assumption, you still get the same solution. That is, all the demand from an OD pair still go to the same path. Okay, a few things to point out. I've given this talk probably 3 or 4 times now, and I get the same set of questions in the middle and at the end. We're only talking about person trips right now. So there's no notion of vehicles in this formulation. Okay, so we're not talking about transit. We're not talking about personal vehicles. We're not talking about ride sharing. We're just talking about people. And also our model, for now, has no notion of congestion or link capacity. So our model possibly could say that we're going to have 1 million travelers on Anteater between 9 a.m. and 9:15 a.m. Our model would allow that, even though that's likely an unreasonable assumption about the system. But just bear with me, and we can talk about the implications of that assumption later. Okay, so for the big picture or cumulative network flow overlap problem, we don't want to just consider flow overlap. We want to consider the trade-off between flow overlap and the detours that the travelers have to make. Therefore, we have an objective function with 2 terms. The first is maximizing flow overlap. The second is minimizing the detours of the travelers. This delta ODK is the detour. And of course, we've already defined Z. And then our decision variable is X ODK. So this is the full problem right here. That is, we have an objective function, which you just saw on the last slide, except I filled in the details for Z ODK with our original definition 4 or 5 slides ago. And then we have one constraint, which is that you must assign the demand from every OD pair to exactly one path. Okay, but we have a lot hiding behind this FAODK variable. It's actually an auxiliary decision variable. We have to decide these values in the problem. And the way this is defined is as follows. So we want to look at every origin and destination pair besides our origin destination pair of interest right now. And then we simply sum the demand from each of those OD pairs by our decision variables and our link path incidence matrix. So you see that we have embedded in our auxiliary decision variable our main decision variables here, which for those of you who haven't picked it up already, is not a good thing, right? Ultimately, our objective function is now going to be a quadratic objective function. We're going to be multiplying our X values by other X values, which is the real computational challenge associated with the formulation of this problem. Okay.
So Mike, I have one
Yeah,
question regarding the formulation.
Mhm.
So there are many ODs,
Mhm.
and this OD, their path may not be totally overlap.
That's right.
So for this overlap, you are considering overlap at the link level.
At the link level, exactly.
So basically, that allows multiple transfers in a sense.
Multiple transfers in a sense.
So I mean, for one OD, then we stop at one kind of those node we consider as a transfer station, and then
Yeah,
have a
exactly.
carpool, and then to another node and then transfer again. So multiple transfers.
Multiple transfers are possible. Remember, we're not talking about, there's no vehicles.
I know, but eventually, if you get vehicle into the picture to implement that, to realize it, sounds like you are allowing multiple transfers. Definitely
allowing multiple transfers, and that's actually, I think, one of the key insights and one of the key contributions of this study compared to the literature is that we do allow for partial overlapping paths because we're doing it at the link level, which we think is particularly critical for the design of a shared mobility network.
Yes.
Okay, so to solve this problem, we use Gurobi. Gurobi is an optimization solver. If you take my courses, we'll be covering how to use Gurobi within Python. It's a constrained quadratic integer programming problem, which is quite challenging. We use network X package in order to define our set of K paths for each origin destination pair. And we're just assuming that there are 5 possible paths between each origin destination pair that one can choose from. We use Yen's algorithm to define or to create the 5 shortest paths in this case, or the K shortest paths in general. We could talk about this later if you want. There's probably better ways to define a potential set of paths besides the K shortest, but for now we're just going to use the K shortest. Okay, so we have the formulation. We're going to plug it into the solver, and we're going to use the Sioux Falls network as our case study. We're creating 3 different sets of scenarios. So scenario 1, we basically just have 6 origin nodes in the north of the Sioux Falls network and 6 destination nodes in the south of the Sioux Falls network. Solve the problem and see how much overlap there is. We're defining a set of scenarios, scenario set 2, as one origin to all 24 destinations. But we're going to do that 24 times for each node. So we're going to resolve the problem 24 times. We're going to see which node has the most overlap in the entire network. And then in scenario set 3, we're going to have 1,000 trips. We're going to keep the origin nodes. I think it's just 6 of them. And we're going to vary the destination nodes in the network. We're going to have a highly clustered set of destinations in the center, or the not that Sioux Falls has a CBD, but you could imagine Sioux Falls having a central business district or CBD. We're going to have 6 nodes dispersed amongst the network, and then we'll have 6 nodes clustered in the south of the network. Okay, so I've covered ZOD, which is at the OD or trip level, and I've also covered our cumulative network level metric, but there are a bunch of other potential metrics that one could define using the formulations you've seen on prior slides. So one might be interested in not just the absolute number of overlap, but the % of overlap for an individual origin and destination pair. Obviously, we're interested in the detour between an origin and destination pair associated with a particular path. We also capture the marginal overlap for a particular OD pair, right? So we have this ZOD-SP, which is what is the overlap if you just assign the travelers to their shortest path. You take the difference between that and your maximum network flow overlap, and you divide that by the detour to get the relative overlap per unit of detour. We could also aggregate all of our OD level metrics that by summing over the destinations to get origin level metrics. And this actually was what Nav was particularly interested in this research, was origin level measures of dispersion or concentration in the demand for the system. You get the percentage for that. And then we kind of have parallel metrics at the network level, right? So we have average network detour, where you're summing over all of the demand from all the origin destination pairs in the network. We have the detour ratio, which is the ratio of the travel costs in the maximum network flow overlap problem compared to the shortest path. And then we have these marginal network flow overlap and marginal network flow overlap percentages. Basically, all we're doing is aggregating up and considering two factors, overlap and detour. Okay, so some computational results. So PMN flop is the pure maximum network flow overlap problem. We don't consider detours at all. Shortest path assignment is, of course, shortest path assignment. And then the by MN flop is where we consider two criteria, that is maximizing flow overlaps and considering detours. Hold on to this result until the next slide, actually. So you can see, hopefully, that compared to the shortest path, where a lot of different links in the network are used, denoted by green, in the pure MN flop case, many, many fewer links are used. So this isn't explicit in the formulation, but it is certainly implicit, is you want to move the demand onto as few of links as possible in order to maximize flow overlaps. And then for the by criteria, of course, it's kind of somewhere in the middle between the PMN flop and the shortest path. You're using relatively few links, but a couple more than the pure MN flop. And these, sure.
I understand that you did not consider the congestion effect.
Yeah.
It looks like that is totally caused by the not considering congestion effect.
Yeah, exactly.
Because you just put all the vehicles on the same roads.
Yeah.
All the time. It has a benefit, on the carpooling on this effect, but definitely cause a lot of congestion.
So I certainly agree, but I guess I'll get into it now. I think, and Nav is going to start testing this in a few months. For those of you familiar with the transit network design problem, one of the most challenging things is getting an initial set of potential routes or lines in the transit network. And I think the output of MN flop can be a very useful input to transit network design, right? Because it's telling you exactly where you want your flows to be, right? But I do agree with Wenlong in general that even if we are assuming this is a fully transit network, you should probably put some capacities on a link, right? Even a rail system has an upward capacity on how many travelers can go over a link in a certain period of time.
So I think it is similar to TSP because we are minimizing the travel lengths of the network. So then we are minimizing the number of links in this case on the right, on the left side specifically. So we are minimizing the number of links and the travel lengths, and pooling like this will be like the TSP.
TSP being traveler salesman problem?
Yes.
But I think in the TSP, you have a fixed number of trips that are made. Because if you have N customers, you have to have N-1 links, I think, in that used between those customers. But I think there's a connection there. I'm just not exactly sure quite what it is.
Basically, without considering capacity constraint.
Oh, compared to a
I
VRP.
understand. Yeah.
The formulation is a date involved, right?
Yeah.
So the results would highly depend on what date you use.
Yes.
Okay.
So here's the Pareto frontier for the weight. So if W in our case is greater than 3,000, it converges to a shortest path. And you probably don't remember, but W applies a weight to the detours. So as W increases, you put more weight on minimizing detours. So this becomes the shortest path problem right here. And then as W is equal to 0.1 or smaller, we converge to the PMN flop. And then we have a number of values in the middle here between the two ends of our spectrum. Which, I mean, usually when you get these Pareto frontiers, there's some useful information. Obviously, the elbow here tells you something. Kind of moving from 0.1 all the way to 600 doesn't provide you much benefit at all in terms of changing overlap, whereas you get a kind of a direct decrease in average detour.
What would you consider as an optimal W in this case?
Well, I'm an analyst or a modeler, so I don't decide what I care about most between these two objectives. And obviously, this is one step away from a design decision. But yeah, I guess I can't answer it. It's a good question, but I can't really answer it. Okay. So just a little bit of motivation, because scenario set 2 is just from one origin to all destinations. This is kind of the general idea here. In cases 1 and 2, you can see that there's the same total number of demand coming out of node or zone 1, that is 90 travelers. But where those travelers go to really matters in terms of your potential overlap or potential shareability in the network. And it's the same idea with networks 3 and 4. Again, we have 90 travelers, and they're very much going to different destinations in a region or a network. I don't have too much time, so I don't, but I'll give you where this study came from, right? So Nav was very interested in where we started on slide 3 or 4, determining where between fixed route transit network and taxis we want to be for a particular region of Southern California or Chicago or a city in India. And we looked in the literature, and there had been some studies trying to get at this. Where's the right tipping point between flexible transit and fixed transit? But they only define this tipping point in terms of the density of demand in a rectangular region without a network. Okay, so demand density is obviously an important parameter, but it certainly isn't fully defining the attributes of demand for shared mobility in a region. So that brought about this study where we're considering demand density, we're considering the directionality of the demand, and we're considering the underlying transportation network simultaneously to create a measure of potential shareability. Got a question? Okay. Yeah, good question. So 30 of the travelers go to B. And then another 30 go to C and another 30 go to D. So they split, but you left 30 travelers behind at B. Good question. And it's the same here as well.
So I think it's very good idea. I'm also thinking about the unit could be a product instead of person, because this is also pooling problem. So I think person is also good, but we can also implement this one
for freight. Yeah. So I guess let you under the hood a little more. We submitted this to Transportation Science, and they claim that people consider consolidation all the time in the freight transportation space. They didn't give us any references. I don't think they really understood what we were trying to do with this study, but I think that others see this as well. That we talk about people, but it could be any flow through a network. Okay, I'm kind of running out of time, but so we can see that for the Sioux Falls network, x-axis is total demand originating from a particular node, and the y-axis is the percent overlap. Left-hand side, we have PM and flop. Right-hand side, we have shortest path assignment. So two main things to look at. That is the difference between shortest path and PM and flop. In general, you get an increase. You move upwards on the y-axis by doing PM and flop. And the other thing is that there's not a direct, super strong correlation between demand density from a node and overlap percentage, right? There actually is some uncertainty there, which has to do with the underlying transportation network and the dispersion of the demand. So this is what two cases look like. So if your origin node is node 2 to every other node in the network, versus the case where node 5 is your origin node and you're giving to every other node in the network. Okay, I think hopefully you've got the general ideas. I'm going to skip set 3 so I can move to the other study. But just as a conclusion here, a bit of a summary. We're saying the shareability potential of a transportation network has to do with the magnitude of flow overlap in that particular network. We have a kind of a complex mathematical formulation that's associated with maximum network flow overlap. Our model is what we're calling both mode and operational policy agnostic, right? Most of the other stuff you see in the literature assumes a particular mode or assumes some type of ride sharing algorithm. Kind of forget all that. This is much higher level. Right? This is what we're calling a fundamental property of a transportation network or of a city. Now, the attributes of the travelers and the attributes of the shared mobility network that you design are going to impact actually how much sharing you get. But this is really a fundamental property of the network and the travelers moving through it. Okay, so extensions, we want to use heuristic algorithms because we can't really solve large problems. We can only solve relatively small problems. And then we want to use this to help make design decisions. I already covered the case for fixed route transit network design, but actually what NAV is working on right now is a transit feeder system where we do have the one to many nodes. And actually, I mean, there's a clear correlation between our measure of shareability and the efficiency of a last mile transit system. Now, the question is, when we put that in a regression model and we incorporate all the other factors that people have looked into in the past into measuring the efficiency of a vehicle routing problem as a function of the network, is our parameter still predictive or still statistically significant? Question from Pengwan. My study, does it consider the travel time differences after transferring? So we certainly don't model transfers explicitly. It's just people moving through a network. And then the travel time, the links are all fixed because there is no mode. Actually, we don't have travel times. We just have travel distances. Yeah.
Mm-hmm. Thank you, Professor.
Yes, but they're all for a particular mode, right? So there's this Santee et al. 2014 paper. You could probably type in that name and shareability. And what they tried to uncover is the shareability potential for a ride sharing service in a particular city.
In this case, let's say you only model, like, okay, you're not considering anymore, quickly might be in this case.
In our case?
Yeah.
We hope ours can inform multiple modes and can actually distinguish where a particular mode works well and doesn't work well. So that would be the validation study for this, but we're working on that right now. We haven't got there yet. All right. Any last questions on this study?
Nobody else has. I have one question. Have you guys considered, the economic? This is related to Kongyan's question. When we consider the travel time, the cost, all into this, and then of course, I understand when we get to this, we need to consider the cost associated with different modes.
Yeah.
Already, but maybe a more fundamental question is related to you said that one is maximize the overlap when you flow. Another is to minimize detour. And that is in certain sense try to minimize some costs already. And these two are kind of conflicting with each other. How did you solve this multi-objective optimization?
We use the weighting approach effectively. We varied W to try to get the
linear combination.
Yeah, linear combination. Yeah.
Because there are different formulations of this. For example, I mean, actually we had one study to use the game theory to consider these two objectives as kind of two players. They are competing with each other. So basically, there can be multiple solutions.
Yeah.
Many different solutions.
There are a lot of different ways to solve multi-objective optimization problems,
I
right?
guess that weight should also depend on the mode eventually.
Yeah, to try to get, I mean, right, when you do multi-objective, what you want to do is get the Pareto frontier, but to actually decide where along the Pareto frontier is meaningful, you have to put meaning behind your weight W. Nav makes good arguments for what the physical meaning of our W is, right? It's the minimum increase in overlap for a unit increase in travel distance or travel time, right? That's what our W means. But what that value should be, kind of, who knows?
Yeah, because in this case, I mean, the unit of the object function did not match basically. I mean, the two.
Oh, they don't. Yeah.
Yeah, then the weight actually should have some physical unit. So
Yeah, it's the overlap per unit detour distance.
yeah, some
So that's what, I mean, one could argue if, people start using our study more, they might gain an intuition of what that appropriate trade-off is. And I think it's pretty clear, right? If you think about Manhattan versus Sioux Falls, we're talking about absolute flows. It's going to be, you're going to design a subway system in New York City, and in Sioux Falls, you're probably not going to design a subway system, right? Which is what occurs right now. The interesting thing is what is in the middle, right?
Yeah.
Should Houston have more transit lines, or should, I don't know, maybe Boston have less transit lines or something like that?
thank you.
Oh, can I do the online one? Should be real quick. So Shenyang Chen, thanks for the question. Does the model consider any matching delay or measured in the case study? No, we don't have matching because we're not doing matching. Yeah, sorry, there's no matching involved here. There's path assignment or path choice, but not matching vehicles to travelers. Go ahead, Arash.
So, at the beginning of this study, you talked about the difference in the networks of Irvine, Heights, and one other place. But in the applied example, in the study was like it's really a small network. I was wondering, what was the simulation time for that small network, and are you considering to apply this method, or are you concerned of applying this method in like mid-sized city and getting the simulation time significantly?
So by simulation time, you mean like computational runtime? Yeah, it's very large. Even for like an 8x8 OD demand. I mean, you can ask now, but I would guess probably a few hours for that. But if you go to like 24 to 24, we can't even run it. Like Rovi won't be able to solve it in a reasonable amount of time. I guess, so the things that matters is the number of origins, the number of destinations, the K paths. You can obviously imagine why those matter, but also what matters a lot is the potential for the K paths between the OD pairs to overlap with each other. All right, so as those overlap with each other, you have many more and more quadratic terms that become relevant in your objective function. All right, many more X ODKs that could potentially be impacting each other. So yeah, I think this calls for some type of genetic algorithm, but the challenge is actually not so much finding better solution, it's evaluating the objective function. Right, so as the ODs increase, as the Ks increase, you just start going from thousands of terms to tens of thousands of terms to millions of terms in your objective function, which is kind of a fundamental issue. So what Nav is talking about doing is like trying to cut terms from our objective function using known attributes of the network, or really only allowing flows from certain OD pairs to potentially overlap with certain other OD pairs, which can really trim the size of the objective function. Oh, okay. Shenyang, that's really good insight. We haven't done that yet, but I think you're probably right. If you assume a fleet size where each individual vehicle has a certain capacity, you could probably infer what the minimum fleet size is for a particular mobility service. All right, I'm going to move to the second study. We only have like 15 minutes, but we've obviously had a lot of questions so far. Okay, so this is work with Arash and again, just kind of a problem that was of interest to myself and Arash and again, no funding, no dissertations, just I've kind of wanted to work on this problem for a while. Okay, and it's fleet sizing for automated mobility on demand services. AMOD here is, you can think about it as ride hailing, ride sourcing with automated vehicles, where the fleet owner, the fleet operator owns a fixed fleet of vehicles, and there's no ride sharing. So an individual trip is made in an individual vehicle. Okay, why does fleet sizing matter? Come at this from two different perspectives, kind of the private company or the public sphere. So from the private company that owns these vehicles, obviously more vehicles means more costs for them. These costs are associated with taxes, interest on the owning of the vehicles. storing these vehicles, insuring the vehicles, maintaining and cleaning the vehicles. And also fleet size has enormous impact on service quality, in particular wait times, right? If you have 1 million vehicles in the network, no one's going to have to wait for a vehicle because there's going to be one relatively close to them. From a societal perspective, the main impact of fleet size is kind of total parking space in a region, right? If we could actually get people out of personal vehicles, or not even out of personal vehicles, but giving up personal vehicles and using a shared mobility service, I think you'll see we'd have a lot less need for parking in urban areas. The impacts on congestion and mobility, I think, are much smaller and much less indirect, much more indirect, because ultimately you're still having a lot of vehicle miles driven in the network, and potentially even more, just with many fewer vehicles. Okay, so to say this is an important problem, many others have been working on it as well. I come kind of from an agent-based simulation background. We've done some kind of implicit work on the impacts of fleet size on performance and cost, but and others have focused more directly on agent-based models for fleet sizing decisions. So the advantages are these are, of course, high fidelity, high resolution models. They can capture congestion relatively well. They can capture stochasticity. They can capture travel demand, behavior, heterogeneity amongst travelers. Disadvantages, computational time certainly is one of them, but I think really the really big downside is how data intensive these are. And if you want to calibrate them accurately, you just need tons of data that's not readily available from any, well, source, any one source, right? If I could get data from Uber, I could get data from City of Los Angeles, I could probably calibrate these agent-based models, but I can't really do that right now. So others have developed analytical, really numerical models to try to get at this fleet sizing decision problem. I'm going to go over the Vazifa method, and we're going to compare all of our results to the Vazifa method. We won't get into the Spicer earth moving problem method because ours is actually an extension of that. We basically bring into the problem formulation a time expanded network. They assume a non-time expanded network. Okay, so we stole this from Vazifa's paper. It's actually a really nice, really simple method. So you can look at the top, but I'm just going to go to the bottom. The top parallels the bottom. So the inputs, there's two of them. There's the trip request. So every trip made in Manhattan over the course of a day. Start time, end time, start location, end location. Got it? Also the travel times in the network. How long does it take to traverse each individual link as a function of the time of the day for the Manhattan network? From these trip requests and from the travel times, you can construct what they call a vehicle shareability network, which is, I think, a pretty huge innovation. They didn't come up with the vehicle shareability network, but other folks at MIT did. Each blue node here represents a trip from this data set. So the node represents all the information here. Origin location, origin start time, destination location, destination start time. What a link represents is, can a vehicle serve this blue trip and then after serving this trip serve another blue trip, right? So basically, is the drop-off time and drop-off location of this trip amenable to the pickup time and pickup location of this trip, right? So where there's not a link, there's no link between these two, a vehicle cannot serve this trip and this trip. Okay. And then once you get your vehicle shareability network, the minimum fleet size problem becomes a path cover problem. Right? You want to cover all of the blue nodes with as few unique paths as possible. So in this case, you have 4 paths, which means your minimum fleet size is 4 vehicles. 1, 2, 3, 4. Okay, so we're going to compare and say our method's better than this one, but that's what every researcher does. But this is a really smart, really, I think, innovative method to model an interesting problem. So it's computationally efficient, and it's really high fidelity in terms of the temporal and spatial resolution of these requests. They're getting the, not exact, but very near exact start times, end times, start location, and drop-off locations, and incorporating that in their decision model. So 2 downsides, they have this parameter delta, which is the only thing that determines whether or not this trip can be connected to this trip or not. And so they just vary it, 5 minutes, 2 minutes, 7 minutes, etc., and they see how the results change. But according to me, this isn't really a decision parameter that mobility on demand operators would decide, right? You wouldn't say, I'm only letting my vehicles drop off a traveler here and then drive only 7 minutes to pick up another traveler. Obviously, that would depend on a lot of factors, how much demand there is in the network at this time, where we expect the demand to be in the future. And then the other downside is when they compute their metrics, particularly their empty miles traveled, they just assume that the vehicle appears at the start of every one of these paths and disappears at the end of every one of these paths. That is, they don't have to go back to the depot or from a depot to start the path. Okay, so what do we want to do? We want to formulate a fleet sizing problem. We want to do it as a network flow formulation, and we want to have a time expanded network. I'll show you what that looks like in a bit. We want to apply this model to a large scale system, and we want to compare our results to those of the path cover or Gazebo approach. And we want to also, because we've seen a second, we're going to be making aggregation decisions both spatially and temporally. So we're going to see how those spatial and temporal aggregation decisions impact our estimates of fleet size and of empty vehicle miles traveled. Okay, so we're going to call our approach the TDTP, kind of the time-dependent transshipment problem is where it comes from. It's really, those of you familiar with network modeling and network flow modeling, it's a minimum cost flow problem, which is displayed here on the bottom left, where you have either a surplus or a deficit at every node in your network. You have the cost of traversing every node in the network. You want to move the flows from the surpluses to the sinks, such that at the end, you have all of your surpluses being used and all of your sinks being covered. And this is an example of expanding a network. So we basically copy the network at each different time period. So this is the network at time period 1, this is the network at time period 2. You can see that the movements through the network actually cover both space and time. So moving from node 1 to node 2 requires a single time period. Advantages, also computationally efficient. Disadvantage, it does require spatial aggregation of the Manhattan network, or any network in fact. And it effectively ignores intrazonal travel distances. So, in some ways it's better than the path cover approach. In some ways it's not as good as the path cover approach. All right, so let's get to the actual problem here. So we're given basically the same information. The travel times, which are time dependent between each zone in the network, also the travel distances, which we're assuming are not time dependent. And then you could also assume we're given the trips, every trip in the Manhattan network. And then we aggregate those into these FITs, which is the number, basically this surplus or deficit at every zone / node at every time period in the entire region. We'll also assume we have 3 cost parameters. We're actually only going to use 2 of those, but the first is the fixed daily cost for having an extra vehicle in your fleet. The second one is the cost per mile driven of the particular vehicle. And then we didn't do this, but you could have a cost for not serving a demand in a particular time period and allowing that demand to go into the next time period. Okay, we want to find the number of vehicles starting at each zone. We want to find the repositioning movements in order to cover all of the demand throughout the day. And then also the surplus or deficit of vehicles from each zone that stays in that zone from one time period to the next. So if we sum over our YIs, that gives us our fleet size, right? That's the total number of vehicles that start the day in each one of the zones. We want to minimize cost. That's our objective. All right, how are we doing on time? Okay, terrible. So some assumptions here. We assume that the occupied trips are fixed, right? From our data sets, we have every trip within a day made by taxi in New York City. We assume that that traveler must be picked up at the time in the data set, at the location in the data set. You can't come a few minutes late. You can come a few minutes early, but you're going to have to wait for the traveler right there. So that means we're only modeling explicitly the empty vehicle movements. We don't need to model the occupied vehicle movements because they're fixed. We also assume that the wait time for the travelers is effectively 0. So this is actually necessary for our first assumption. It's necessary for the first assumption because, well, if you're assuming that the occupied trips are fixed, then the vehicles must be there at the beginning of the trip. And then also this is necessary for apples to apples comparison with the path cover approach, which also assumes a wait time of 0 minutes. Okay, so not really assumption yet, but just a statement. In any mobility on demand service, there's 2 types of empty vehicle miles traveled. The first is the explicit repositioning of vehicles from one zone to another. We capture that in our model explicitly with these XIJTs. But then there's also the empty pickup trips, right? So even if you do a good job of repositioning your vehicles throughout the day to make sure they're near where trips are going to occur, once the request comes in on the smartphone, the vehicle still has to move a little bit to pick up that trip. So this model does not explicitly capture this portion of empty vehicle miles traveled, but we have a way to add this in to get better estimates of the total empty vehicle miles traveled across these 2 types of EVMT. Okay, so again, I like simple formulations. This is a simple formulation. We have an objective function, which is to minimize the weighted cost of vehicles, summing over the yi's times the fixed cost associated with each one of those, plus the empty mile travel cost on the right-hand side. We have our flow balance constraint actually in this network because we're dealing with flows of vehicles through our particular network. This is a relatively complicated one because you have the time dimension in this flow balance constraint. And then I have a separate flow balance constraint for the first period, which just makes a direct connection between the y values and the z values and the x values. You could actually easily formulate this problem such that you only have x's, but we want to have y's and z's and x's to, well, make it easier to communicate what's going on in the model, as well as make it easier on ourselves to process the output. And then in order to ensure that the wait times are 0, we make sure that the number of vehicles in zone I at the end of the prior time period is greater than the demand for vehicles in that same zone in the next time period. Right, so let's say FIT is equal to -5. That means we have to cover those 5 travelers in time period T in zone 5. To do that, I'm going to make sure that there's at least 5 vehicles waiting over in this zone from the prior time period. Okay, so we're going to go through 3 steps of this problem with an illustrative example, and then we're going to do a big network here. So this is the demand. We have our time periods T1, T2, T3, all the way to T5, and then let's just say we have 3 zones, 1, 2, and 3. Right, so you can have, and these are the actual occupied trips. Trips from zone 1 in time period 1 to zone 2 in time period 2. There's 2 trips. You can see we actually have 2 trips that start in time period 1 and end in time period 2 for the same zone. Right, if these zones are particularly large, they can move across that zone in the same time period. What other information is on here? Yes, this is just the trips between the zones. So we need to process this kind of raw input into the inputs we need for our formulation, right? So what we need are these FIPs, which is the relative imbalance of flows going into and out of these nodes, where our node represents a zone time pair. You can see we have positive values and negative values. Notice that on the left-hand side, you tend to have negative values, right? Because this is the start of the day. You only have trips leaving these zones, right? And then towards the end of the day, it tends to be positive because most of your trips are terminating at the end of the day at a particular zone. You can also see what our decision variable values are as well, right? So Z is how much it's staying in zone 2 from time period 2 to time period 3. And then the X's are the dash one, which are the movements between the zones across time periods. Not labeled here are the link travel times, or excuse me, the zone to zone travel times. So we also have those as well. And then here's what the solution to the illustrative example looks like. Right, so we actually only have one repositioning movement, which is repositioning a lot of vehicles from zone 2 at time period 2 to zone 1 at time period 3. Otherwise, we just have a lot of vehicles in each one of our zones to start the day, and those vehicles just cover the demand for the rest of the day. And what is our fleet size here? It's 55 plus 4 plus 20, which gives us 79 as our fleet size. Okay, so we did a case study. New York City, lots of vehicle trips, 3 different temporal aggregations, 2 different spatial aggregations, and we compare these with the ZIFA approach. So computational time, which is a particularly important factor if we're arguing we don't need agent-based models. Well, okay, how much time does it take to solve these? So this is in seconds, all of these values. You can see that if we have a relatively large spatial aggregation, which is the census tract, for our problem, it's about 1/10, 1/20th of the time of the path cover approach. But if we have a finer spatial resolution at the census block group, then our computational times are actually slightly larger than the path cover approach. But on our end, we can control this, right? We can select how big our zones are. So depending on how much computational power you have and how much time you have, you can choose what is an appropriate zoning system. Okay, what about our estimates for fleet sizes and empty mileage? Okay, so let's start with fleet sizes on the bottom. They're the same order of magnitude. They vary across the values for temporal aggregation as well as across the spatial aggregation. So, right, none of these are the right answer, right? We can assess them on whether or not they're reasonable, and we're going to do that in the next set of slides. But there's no ground truth to compare these against. At least there's no ground truth yet. So one of the next parts of our research project is to compare these estimates against an agent-based simulation to see which of these aggregation levels and which of these methods provides a tighter bound for the minimum fleet size. Okay, so 2 things we looked at is what's the relationship between the fleet size, minimum fleet size? Yeah, go ahead. Question?
In the spatial aggregation, even in 10 to 15 minutes per census block group, right? But time before this.
Yeah.
How much time does it take to cover one given block? Like, what is the maximum on?
Less than 5 minutes, I think, in like 98% of them. Yeah. Good question, though. I think maybe Ross can talk to you afterwards. We did put some thought into that, but I can't remember how we ensured it.
I thought that it was 10 minutes, then you did a time aggregation of 10 minutes.
Yeah, good question, though. So we solved this problem, and we wanted to see if there's a direct relationship between the number of taxi trips and the fleet size. You can see from the R² values, kind of for any of these methods, there's not a particularly strong relationship between number of trips and the minimum fleet size. This is expected, right? It shouldn't be as simple as counting the number of trips, multiplying it by some factor, and getting your fleet size. These trips, they have different spatial temporal distributions, and they also have different lengths. So it's not really a good measure of the demand. A slightly better measure of the demand to make the connection with the fleet size is what's the total occupied VMT, or the passenger miles traveled in this system. So that's our x-axis, and the y-axis is the minimum fleet size. You can see that the connection is actually reasonably strong for our approach with 15 minutes census tracts. The connection is a little bit lower with our approach with census block groups. And then with the path cover approach, there's still a lot of scatter between these 2 values. So we still don't think that this value can be used for decision purposes quite yet, because this still doesn't incorporate the spatial temporal distribution of the demand. Right? It only is just a measure of how much vehicle miles traveled occupied there is on the demand side.
So this actually kind of makes sense, right? Because in the network, VMT is a better measure of demand. that
Right.
each counts. Okay,
Exactly.
we had this discussion.
Exactly.
all along, right?
Yeah.
Yeah, you might not agree, but this is another.
Point in your favor, yeah,
Yeah,
exactly.
right,
But it's not everything though, right?
I know,
Yeah.
but this seems to be, it makes sense,
Improvement,
right?
yeah.
Not only the number, it's also the length.
Exactly, yeah.
I just so mentioned.
So this kind of is that same set of results in a different way. So we have two y-axis. The right-hand side is the number of trip counts. That y-axis is only associated with the dashed line, which is the number of trips. The left y-axis is the fleet size, and then the x-axis is the days of the month. So days 1 through 30. I've circled the Sundays. You can see that the Sundays have almost always the lowest fleet sizes, despite not necessarily having the clearest or obviously the fewest number of trips. Right, Sundays are pretty low in number of trips, but here Monday has fewer trips than Sunday, but Sunday has a much smaller fleet size, which has to do with a couple of things, but one of them is obviously the length of the trips. So apparently the lengths of the trips on Sunday are much smaller than the lengths of the trips on Mondays, and the spatial distribution of trips is also different. Okay. So, sorry. Obviously, something that matters is the empty vehicle miles traveled in these systems. We want to estimate how much empty VMT is required to cover the demand. We look at two different spatial aggregations for our method of 15 minutes. And then with the path cover approach, we look at two different values for this interconnection time. And I hope here you can see that the dangers of choosing this interconnection time. So if you set the maximum interconnection time to be 5 minutes, you get really, really low estimates of empty VMT, which I think from all the simulations I've seen are unrealistic estimates. Whereas if you have a large path cover maximum trip interconnection time, you both have high variance across the days, and I think slightly unreasonably large values of your empty vehicle miles traveled. Whereas our approach, I think is actually, from what I've seen in the literature and my own simulation studies, are a pretty good estimate of what the empty VMT would be. Okay, and then I think this will be the last set of results. Arash and again have been working on this for literally months. One of the nice outputs of our model is that we have conservation of vehicles throughout the day. And we can tell you at any time step within the day, whether it's every 5 minutes, every 15 minutes, exactly how many vehicles are occupied, serving travelers, how many vehicles are idle, how many vehicles are repositioning. And that always adds up to our fleet size value. The path cover approach does not have this property. So there's some interesting things here. One of them is that the repositioning values are always relatively low. Another thing I think is interesting is the gap between the maximum number of with passenger vehicles and the fleet size, right? So there's always a gap here, pretty large one, which suggests that just looking at how many trips are being occupied at a particular time doesn't give you the best estimate of fleet size. Okay, yeah, contributions. We, the analyst, has control over the model resolution with this approach, which I think is nice. Another thing I didn't mention is that our problem scale is independent of the number of trips taken in Manhattan. Whether it's 10,000 or 10 million, our problem size is effectively the same, right? Which is, I think, particularly nice as more people start using these shared mobility services. And then what I just mentioned, we can serve the vehicles over the day. And I think one of the outputs of that is better estimates of empty vehicle miles traveled. All right, thanks for letting me go over a bit, and I'm happy to take any more questions. You can probably moderate my own questions if you need, but
Oh, no, that's. I mean, it's up to you.
doesn't seem like anyone's on this or anyone's
All right,
asking questions.
let's check the internet here. Let me start share.
Then I'm using all the time. So, yeah, one question for the second one, the fleet size problem. So here I understand that you don't, you assume the waiting time for the passengers is 0, but in reality, during the rush hour, that's almost impossible.
Yeah,
So I'm wondering what if we allow some level of waiting, how the solutions will look like, how the problem, what kind of extra challenges this would be, and so on.
So originally I formulated the problem such that wait time was endogenous. So we can do it. But I think you would need some type of like fixed point formulation where you have to iterate between repeatedly solving this minimum cost network flow problem and then evaluating the wait time from the prior iteration. I have an idea for how to do it, but it's quite challenging and much more computation intensive. What we'll do to the solution, I think you'll just need a relatively smaller fleet size, right? You get more flexibility in how you cover the demand.
And maybe this is related to the setup, in the setup, for one trip request, definitely, I understand there's a starting time and requesting time and the origin. What is the time at destination? I actually do not fully understand. I mean, is there desired arrival time or what?
So we just take it from the data,
Yes.
or do we take it from the data or do we calculate it?
How
We take it from the data, right?
only request, how do we specify? Do we tell them when we want to buy this? I do not get that.
So here, I got it. So,
There's a destination, but how do we define time at this?
so with the New York City taxi data, right? We're given the pickup time. We're just assuming that's the
That
request
is the
time.
real words.
Yeah, yeah.
That is actual.
Yeah.
May not be there to die.
Well-
Maybe to allow some waiting, we might need us.
Oh, how about downstream constraint? Yeah, exactly. That would be even more challenging than allowing flexibility in the wait time would be having a constraint on the destination.
Okay, I got it. I think that's related to that. Thank you.
I might have one on that.
I think that's just see right, wouldn't,
Okay.
yeah. Are there any questions online? We can get to?
From my understanding, the fleet is several vehicles from one company or one location. I don't understand the fleet size. Your fleet size is actually the trucks in a sense block in a certain time.
Okay,
Professor Hyland, you might want to repeat the question for anyone else.
yeah, sure. The question was, what is my fleet?
Yeah.
I think my answer will probably give more insights into the question as well. So we are talking about a single mobility on demand operator. So you can think about this as Uber, but of course, Uber has flexible fleet sizes. We're assuming they have automated vehicles and they have to choose how many automated vehicles for the whole day up front. There's no flexibility in their fleet size. And then we're keeping track of how many vehicles are in each zone throughout the day. But the main decision metric or the main decision is how many vehicles to start in each zone at the beginning of the day. Okay. Sure.
Do we solely use Groby or just solely?
Garobi. Yeah. Yeah, it's a standard minimum cost flow problem. Garobi handles it really well.
Your daytime is just like matter of changing the network prior optimization.
So say that again.
If you want to include daytime, it's just a matter of changing the network prior optimization. Before optimization is changing the network. The network is half time with them, so there's this matter of changing the expanding the network.
Yeah, I forget how we did it. The one thing that we kind of skipped over, which was quite challenging, is that you need to know when the vehicle will arrive at each other node downstream time, right? And if you allow wait time in a particular zone, that ultimately changes at what time period that vehicle will arrive at the downstream node.
You still would know when it does. So how does it change?
Well, if you
Daytime would come before picking up. So you still know when it will start.
no, because well, you know when the trip wanted to start, but you're now saying that it started later.
Yeah.
So actually, I think you had the right idea. When you bring in wait time, you change the construction of the network.
Expanding the network.
Yeah, definitely. I mean,
And if
it's a common problem.
Then
You will have more possibilities.
There's more viable.
Yeah.
Links in between.
yeah, so you could do it that way. You could super expand the network.
Yeah.
I wanted to kind of keep the same network, but just resolve it by changing the wait times on each, by changing the downstream node that it gets to.
And that way involves some complexity. There's multiple ways, then later it's not possible.
I got a question about, do we find any super unshareable networks? We haven't looked at too many networks, unfortunately. We looked at Sioux Falls, parts of Chicago. I think we're gonna look at Anaheim. We haven't had, we want to do a network comparison, but really the distribution of the demand matters a lot. So we can easily construct instances within a particular network that are very unshareable.
I have a following question on the demand patterns. How can we say that the demand pattern we choose are good representative? Or
For the first study?
yeah,
The second.
first study.
Well, okay.
Or is there a way that we say, oh yeah, after we analyze this case, we probably covered 80% of the demand pattern?
Well, we're always covering all the demand. We always allow people to go through the network.
Yeah, I mean, 80% of the demand distribution of demand patterns, you analyze from the top from north to the
Oh, yeah. So, okay, yeah, fair. Those I think are explicitly not realistic demand patterns, and because we wanted to show that our metric changes as you change the demand patterns. We wanted to verify that it does this, which is a good thing. Now, but I think this gets to the question we just got on the Zoom. I think I promoted this as a way to compare across networks, right? Which we haven't really done yet. But I think it's certainly going to be able to compare across networks. And then I think it's obviously hard to get the accurate spatial distribution of demand, but there are methods to do it, right? This is a whole demand forecasting area can create OD trip patterns. Now, whether or not those trip patterns are going to stay the same as you change your shared mobility modes in the network is another question, but for now we're assuming they're fixed.
I have the following question for the second study. So we are trying to find an upper bound for the for this fleet sizing problem, and how tight the bound is as opposed to the simulation based approach.
We want to find
in terms of the cost, how tight the bound is.
So we're solving the minimum fleet sizing problem. Okay, actually it's more complicated than that, but let's assume we're solving the minimum fleet sizing problem. And then we want to find the best bounds for the minimum fleet sizing problem. I don't have a great sense right now of what the gap is between your fleet size you would need in the real world versus the fleet sizes we're estimating. Here's the things that are not captured in our model, right? There's stochasticity within day that we're assuming away. So that's, I don't know what the multiplying factor is, but maybe like 1.2, right? If you bring that in. There is driver uncertainty. There is traveler uncertainty, right? So these things are all going to start increasing the fleet size required to serve the demand. So then the question might be, what's the point of this model? I think the point is, right, if I'm Ford, if I'm GM, if I'm Waymo, if I'm Uber or Lyft, and I'm developing automated vehicles to put together in a mobility service for maybe the city of Miami, if you have a good estimate of the demand, this model can tell you, you're definitely going to need this many vehicles. Just like point blank, you need this many vehicles. You're most likely going to need more to serve that demand. You can start by, basically manufacturing this many vehicles to serve the demand in a particular city.
Actually, I might not agree that we need more vehicles. were to solve here.
Okay,
Because, since you are using the real world travel data, and in the real world, there's a congestion, hyper congestion.
Mm,
And if there's a way that we control the number of vehicles running the network, actually, we will be able to improve the mobility, increase the speed, and shorten the time and so on. Actually, we could totally have much fewer vehicles to serve all this.
you're absolutely right. Yeah, because as you said, our link travel times are coming from the current system. And we're assuming that we lose that capacity from the vehicle sitting in congestion. So if you could bring down the congestion in the network, you would need fewer vehicles for sure.
Yeah,
I just haven't seen any successful approaches to reducing congestion in many places, right?
yeah. I mean, theoretically, we can, cap the fleet size.
Yeah, of course. But how much does capping the mobility on demand fleet size matter if you have a lot of private vehicles?
Yeah, that's a very.
I think people probably want to go to lunch or something.
Any further questions? Why was the metrics and specific metrics used for shareability required? Because it seems,
So why was flow overlap used?
yeah, like that specific mathematical formula was.
Well, okay, so great question. Right, so we started at a conceptual level, right? We want to get this measure of shareability in the network so that we can make inferences between our measure of shareability and the viability of particular shared modes, right? So I think that's reasonable, right? You want to be able to make this connection. And we wanted to incorporate the underlying network and the demand patterns, not just the demand density. Because we started from there, we then kind of wrote out a definition, which was associated with this unit flow. And I mean, we at least convinced ourselves in our own heads, Nav and I, that our formulation is the best match with our English definition of shareability, right? Which is the flow overlap, the link weighted average flow overlap for a trip from its origin to its destination.
Hiding the distance.
Oh,
It's a link distance, percentage of link distance.
we have link distance, yeah.
Take the difference thing, graph network, and time. Work in that.
So time's more important for detours for sure, but not for overlap from a design perspective, I don't think. Particularly if you could assume that you have bus lanes that are separate from regular congestion.
So it's meant to create a transit network rather than a smaller mobility, like a smaller sharing.
It's meant to capture all the above, but I think in my most recent response, it would imply that we are certainly interested in the fixed route transit network. So I make a quick comment, which is like, this is definitely the most out there research I've ever done. I say it's like the highest variance research I've ever done, because I think it could be like a real game changer in how people think about transportation systems and their potential shareability. Or it's just zero. Like no one uses this ever again. It's too hard to solve. It's too complex for real world networks. I mean, of course, I hope it's on the one end and it really helps people think better about the properties of the network. But it's kind of a wait and see. It's under revision in Part C now, so I think it has a good chance of getting published.
Yeah, actually, following on Chen Yin's comment, it looks like these two problems actually are maybe dual to each other, in the size and the overlap problem.
Oh yeah, there's definitely something there.
I think that comment was really
Yeah, exactly. Because if you know the demand on the links and you know the vehicle capacities, there's definitely something you can definitely infer some fleet size out of that.
It's something for them.
Yeah.
That would be
Any other questions?
you have a OEK value that one that is that is the big size,
What's that?
the OEK value, the small OEK. And that you can directly. It is divided by capacity, you get a big size. OEK basically from 4 to D to K.
But that would just be to cover the demand from that OD pair, but right, we wanna think about the links.
If you just sum it overall case,
Well, you're only choosing one K. K is the
if you
path.
count all ODs, then you just count all the
Well-
total number of vehicles in K.
Yeah, right. So we have the link flows, which is summing the FODKAs over all the ODKs. So that's the only thing left is the A. We can get the flow in each way. I think that's what I was trying to say.
K is the path, it's not the-
K is a path, A is a link. We want to sum the ODKs over the links.
All right, Vicky, did you?
I did. Oh, that's forget about.
Before we would let the audience get moving first. From the sheet.
She wants you.
Probably relevant to that.
Sure.
So I'd like to thank everyone virtually who attended, like to thank on behalf of ITS and all the faculty, staff here. I'd like to thank you for coming. I'd like to thank Professor Hyland very much for sharing his time with us. You were an incredibly engaged audience and I'm thrilled to see you. For those of you who don't know me, I'm Vicki de Guzman. I am the Assistant Director for Programs and Engagement. So this is a very engaging program and I'm thrilled to be here. I'd also like to, for all of you, I would like to encourage you to join us next week, same time, also hybrid, where we are going to spotlight the research of our undergraduates who've been working this summer on research projects. It's so important for me and the students for you to come if you can. These are undergraduates who are in a stage that you were a few years ago, thinking about their careers and trying out their hand at research. And what I'd like to ask the students in the room, the graduate students, I'll be sending you an email with their presentations. And I would like to ask if you could please look at them and give me and them some feedback and plan to engage with them next week. It's just critically important. It's I know I don't need to tell you as researchers why that's so important. For the people in the room, I'd also like to thank you for trying out our new name tags. It's as much for me as anyone. As you know, I'm a little new in my role, and it's really helpful for me to have a visual to get to know all of you. So again, if there's nothing more from anyone, I will thank you all for coming and look forward to seeing you same time, same place next week to encourage our undergraduates in their research endeavors.
Thank you. And we also have a thank you.
Thanks so much for setting this up.
Thank you. Thank you.
I think I got more out of it than everyone. So, my benefit.
They're always good things.
Shall we take?
We have some questions, that's for sure.
Let me take a picture.
Whatever you think, yeah.